It's good.
Right, we're starting. Excellent stuff. Thanks for the introduction, Barry. My name's Paul James. I work at the Technology Centre at Ratcliffe, just outside Nottingham. The legend of Robin Hood continues. Sadly, the castle vanished many years ago, so a bit of a disappointment if it's on your bucket list of tourist destinations. The department itself has been around for some 50 years, just over 50 years, with a heritage that goes back about another 15-20 years beyond that, essentially providing the scientific, technical and engineering support to the CGB, as was Uniper today. The organisation for which I work is essentially a successor company, albeit several generations down the family tree on that front. Today's presentation is at Barry's request on issues of zinc that we found on some pressure part components. Some 40 years personal experience in looking at boiler components in various stages of distress, and access to a library archive going back some 70+ years. The power plant itself still manages to throw a curveball, despite the fact you think that you've seen most of the issues which are likely to affect these bits of kit, and essentially proves that every day is a school day. And the subject of today's presentation is a recent example of such an occurrence. To progress further, a bit about the organisation. As I say, Uniper is based out of Germany. Heritage going back 100+ years, although in the UK our heritage goes back probably more recently than that, in sort of the late 1950s. Range of plants, broad range of broad portfolio in terms of the processes of generating power, and across large stretches of the globe with that. The power plant itself in the second half of the 20th century progressively achieved improved performances through increases in final steam temperatures, as well as increases in the operating pressure. Most of this was fairly progressive, although obviously Edison in the late 1950s was something of a jump, and perhaps a jump too far. But we've now arguably approaching that once again, and there are plants out there which are planned for 2030 and beyond, which will exceed those aspirations from that time. This largely relates to coal-fired plant, but we're now seeing exactly the same kind of processes taking place, at least in the UK. In the HRSG, the combined cycle gas-fired power plant, and we're seeing the next generation high efficiency gas turbines on several of the plant which we support. A recent upgrade at one of these saw a GT26 upgraded, and this has given significant commercial benefits in terms of delivering a 2.5% improvement in efficiency, now tapping on 60%, and it's increased the total output from the plant from just over 400 megawatts to 450 megawatts. Inevitably, there's always a downside to the plus. In this case, for the HRSG, it's an increase in the gas outlet temperature from approximately 620 degrees centigrade up to 650 degrees centigrade. So quite a pronounced increase. Going back to Jeff's presentation, in part, if you like, for each 10-degree increase in metal temperature, you might expect a 50% or halving of the creep life. So quite significant implications for the components. In this particular plant, the final stage superheater, which was going to be exposed to the initial exhaust from the turbine, is fabricated in grade 91, and it's already seen a significant amount of life in operation, and so there's a good part of its creep life which has already been consumed. So the decision was taken to upgrade, and it's a question of which material you look to choose in delivering that. In the end, the decision was taken to go from grade 91 to grade 92, essentially to anticipate the operation of this plant beyond 2030. The coal-fired plant in the UK will essentially cease to generate from 2025, and perhaps even earlier than that. Currently, the Ratcliffe power station is likely to be the only coal-fired plant still generating power in the UK by the end of this year. Grade 92 wasn't the only option, as the demands of power generation or the improved performance have been seen for both coal and gas-fired plant. A range of materials are now available, whether it's from the high-grade nickel-based alloys, the stainless steels, and now the superferritics, one in advance of the fairly basic T22, T11, and the chromoly steels that were available in the first part of the 20th century. However, for ferritic steels, the dual challenge of meeting the basically more onerous operating conditions, particularly pressure and temperature, as well as quite often corrosion performance, have largely been met through these ferritic steels with increasingly exotic additions to them. And as they become more exotic, so they become more sensitive to the quality control implemented during the fabrication stages, both in the workshop and on site. And this is largely shown on the right-hand side, a schematic which has come out of Germany, and is largely related from the carbon steel, the parents of the materials of their forefathers, through to the grade 23, 24 at the top end, which are proven to be particularly problematic on plant in the US as well as mainland Europe. We've hardly been here once before, though. The introduction of stainless steels in the UK followed its earlier introduction during the 1940s and 1950s on US plant. The plant in the US was operating at 540 centigrade. In the UK, it was 560, 570 degrees centigrade. And as a result, we saw very early issues with weld cracking local to the outlet headers, at transition pieces, and also at welds in the main steam pipe work. Ultimately, when you do the sums at the time, it probably came out to about $6 to $8 million. Today, it's probably closer to $100 million during the 5 years leading up to its final resolution in the 1959. This was largely addressed through changes in the consumables which were used, the improved stress relief procedures which were put in place, as well as better inspection procedures and post-weld surface dressing that was put into place. We've largely seen these kind of approaches taken for the more exotic grades, but whereas grade 23 and 24 are sort of the new kids on the block, if you like, grade 91 has got rather more of an established history, but it's come with its own issues. Perhaps the first of these was during the mid-1990s. Grade 91 was seen as being the answer to a maiden's prayer as the UK industry saw a transition from baseload operation to cyclic operation with the introduction of gas-fired power plant. And a particular example shown on the screen now is the loss of an end cap fairly early on in the life of a component. Certainly the design didn't help either the assembly or certainly the inspection afterwards. And as further investigation progressed, it was quite clear that the alloy composition wasn't necessarily ideal. I know people such as engineers such as John Parker have sort of laboured on about essentially narrowing down and being very precise with the composition of these alloys. Post-weld heat treatment has also not always been ideal. Somewhat cavalier approaches taken by contractors has led to hardnesses in excess of 400 Vickers relative to the expected values of around about 200. In this particular example here, in an evaporator tube, we saw a stress corrosion failure. I've put 48 hours. The reality is that the failure probably occurred in a 7mm thick component in the space of 6 to 7 hours. So it can be very rapid if you get things wrong. And in issues where the contractor's not necessarily got the fabrication quite right and sought to correct their errors through the application of techniques used by the materials of yesteryear, such as the T11, T22, you can get marked changes in the microstructure, which once again will either lead to premature failure through creep or other damage mechanisms like stress corrosion cracking. The example shown here is also worth noting that a cherry red in a component isn't necessarily the same in a well-lit workshop as it is in a dull workshop. We've also seen issues with combustion in some of the coal-fired plant, which has meant that the grade 91 tubing has seen transient temperatures up towards 700 degrees centigrade. Multiple events such as these have tended to rob the grade 91 material and taken it from the mechanical, the high temperature creep properties of a grade 91 down to a grade 9. What I've often described as rather like cutting Samson's hair. The material ceases to behave as it was intended and the result of this is premature creep failures, as highlighted in the illustration. In a presentation that I saw Jeff Henry give a number of years ago on US experience related to the spallation of steam side oxides on grade 91. Already well recognised on austenitic stainless steels, this has become more of an issue on recognised issue on grade 91, not purely in the US, but there's also been a few examples noted in mainland Europe as well, with implications for downstream components more than necessarily the grade 91 component itself, resulting in erosion damage to valves, to bends in drains, strainers, as well as turbine blades. Certain design features may also hinder inspection where there's known problems with grade 91 itself, a particular example being shown here with the reinforcing pad being applied onto the branch weld. And whether the inspection engineer, the design team were actually intended the inspection engineers would be elves and pixies, I'm not quite sure. But certainly a fully grown adult tends to struggle getting around most of the parts of the HRSG these days, particularly in the dead spaces. And there have also been instances where grade 22 components have been replaced with grade 91 in anticipation that this will greatly extend the life of the component under a cyclic operating regime. Instead, what we've ended up with is replacing the star cracking around stub welds, often with the circumferential cracking at the same stub welds on the external surface, often resulting in very little extension in the component lifetime. But the topic of today's talk is mainly the effect of zinc paint on grade 91 HRSG components, something which we've discovered in the last 5 or 6 years, and has subsequently raised more than a few ripples on the international scene. The tentative steps taken towards identifying the problem were made in 2016. Colleagues at Technology Centre were involved with the routine integrity assessment of a grade 91 steam outlet branch, and this revealed a dark etching band adjacent to a weld, as shown in the central of the 3 images down the bottom. This was within the outer heat affected zone adjacent to the parent and slightly remote from the fusion boundary. Material analysis was undertaken in situ, and this confirmed that the dark band itself was zinc enriched. And when further investigation was done on the background to the component itself, it was found that rather than typical red oxide coating, which has been long established and it's certainly been tried and tested, the component itself had originally been coated with a zinc paint, in this specific case an ethyl silicate based elemental zinc paint. But what we've discovered subsequently is this is not unusual, and this is a fairly regular practice which has been undertaken in the last decade or so. The dark band itself was fully circumferential around this weld, and there was also signs when replication was the replicas were examined of creep cracking and cavitation, all within this dark band, and also at the flank position, the type 4 position, which Jeff mentioned earlier, position where you'd expect creep damage to develop, but this was decidedly premature and not really seen on other plant. So what of zinc itself? What is it? Why should we be so concerned about it? It's generally pretty benign, and it's seen around the patch. It's a bluish white metal. It's got some ductility with it, and it's got relatively poor corrosion performance, which largely makes it ideal for sacrificial behaviour such as in galvanised components. So it's well known around power plant, it's well known on chemical processing plant. It's even seen in the home. It's also got a very low melting point at 420 degrees centigrade, hence the use in hot dip galvanizing. But perhaps its position in the periodic table gives a few clues as to why there might be more concerns about it than purely the behaviour which is described there. Next door to the right, you see gallium. Certainly not a material that you would like to take onto an aeroplane that's got an aluminium substructure to it due to the risk of liquid metal embrittlement. And to the left, we have copper, which has been seen on more than one occasion on power plant, where the melting of copper deposits on the internal surface of the component has led to liquid metal embrittlement. Liquid metal embrittlement itself is the rapid brittle failure of what would normally be considered a ductile material. The liquid metal to which it's exposed will tend to migrate along the grain boundaries within the component under a stress. And effectively, instead of having a steel component, you might as well have a length of copper pipe, because those are the mechanical properties which you'll be expecting. As highlighted in the illustration here, the intergranular cracking is essentially decorated with the active metal. As I say, copper is a relatively regular visitor when this mechanism is identified. What's shown here is exceptional. This is an example from the mid-1970s of a stainless steel reheater tube to which a thermocouple was attached using a galvanized clip. Operating at temperatures up towards 600 degrees centigrade caused the zinc to fuse into the tube wall and result in failure as shown here. What we do recognise is that austenitic stainless steels are vulnerable to zinc liquid metal embrittlement. The question is, are ferritic steels also, with respect to the grade 91 that we were seeing? Just as a bit of background for the kind of issues that we potentially can encounter, this is the Uniper chemical works at Flixborough in the UK in May 1974. The plant itself produced caprolactam from cyclohexanone, and this is used in the manufacture of nylon. On the afternoon of the 1st of June 1974, this is what it looked like. Pretty catastrophic failure. The explosion associated here caused damage to properties up to 3 miles away and could be heard 35 miles away. Almost reminiscent of the Brockton shoe factory back in Massachusetts back at the start of the 20th century. Investigators subsequently identified that a local fire caused melting of zinc galvanizing on steel components above a 316 stainless steel pipe. This piping connected to reactors and was carrying cyclohexane. What they established was that the stainless steel pipework had failed by liquid metal embrittlement associated with the zinc dripping down onto it, leading to the catastrophic failure which you can see. The incident itself killed 28 people, injured another 36 from a total weekend workforce of 72. Gives a measure for the scale of devastation which was seen there. Other examples during the construction of a chemical plant, which I found online, type 304 and 316 stainless steels, which piping was used and then welded on site to structural steel work, which had been galvanized. Oh, sorry, not galvanized, but painted with a zinc-rich primer. The piping was then welded into place and hydro-tested. During the hydro test, they experienced multiple leaks, with the NDT revealing afterwards that the cracks themselves were intergranular and adjacent to the weld passes. The laboratory investigation confirmed zinc in the cracks adjacent to the weld passes, and the whole process itself was attributed to liquid metal embrittlement, similar to what we've previously described. The cracking coinciding with positions where the stainless steel pipe surfaces had been coated with localized splatters from the brushed or sprayed on zinc-rich primer which had been used. A third example was during the hydraulic test of stainless steel tanks, where there were leaks detected at almost every level where a galvanized steel ladder had been welded directly onto the tank walls. Once again, liquid metal embrittlement was implicated. And it's generally considered good practice whenever welding galvanized components, particularly to stainless steel, to require that coating, the zinc coating, from the component prior to welding, although noting that it may not always be possible to actually completely remove effectively that coating from the surface. That may still be a slight residual risk. Back to where we started with the steam vessel on which the dark band had been identified. Investigation continued. Colleagues at the Technology Centre at Ratcliffe found dark bands in the heat affected zones of numerous surface replicas from several P91 components. And once again, they found high levels of voids in the dark bands which had been seen there. What seemed to be apparent was that the presence of zinc in this dark band was making the material more susceptible to creep damage. And following examination of a boat sample, once again echoing comments that Jeff said about the value in taking boat samples where concerns are raised, the banding was again confirmed to be a localized region of zinc affected material, confirming the on-site observations. However, the zinc itself was seen to be intermetallic and not liquid metal embrittlement, as initial concerns raised. Several theories were offered up as the potential cause of this banding, particularly with possible effect of heat treatment which had been applied to the welding. But what we saw was it was largely a surface effect. The particular example shown here in the grade 91 steel, shown between about 100 to 200 microns in depth. Where it's been observed in 2 chrome components, then typically it's perhaps been 1 millimetre or 2 millimetres deep. But all the concerns that we had were related to the grade 91 components. In seeking to explain how the zinc got into the heat affected zones, what was apparent was that the weld preparations had been painted with zinc prior to fabrication to offer some level of corrosion protection. When welding was achieved, the material immediately adjacent to the weld itself, local to the fusion boundary, saw the zinc vaporizing off at temperatures above 900 degrees centigrade. However, within the intercritical heat affected zone, the zinc would have been molten and rapidly diffused into the material adjacent to it. Just to note there that the AC3 and AC1 temperatures there for the different zones, which you can see in the photograph here, highlights how you've got that temperature zone between about 800 degrees centigrade up towards 900, where we're seeing the diffusion. And it's also reflected in the very skewed bell-shaped curve that we're seeing here with the coating. So for ourselves within Uniper, the Technology Centre, it became apparent that we required careful analysis of the surface replicas that we were obtaining, not only to identify whether there was a presence of a dark band local to the weld, but also to understand the true extent of the creep cavitation that was being seen there. This was reinforced by an incident on the European mainland, where an example of the localized coating associated with zinc paint seemed to act as something of a metallurgical notch, potentially prompting or initiating a crack from the external surface to go through the component. Once again, there was creep cavitation noted within the zinc-rich zone highlighted in the schematic, the photograph on the right-hand side. So within Uniper now, the current procurement specification explicitly prohibits the use of elemental paints. This may require quality control checks, but you still see it on some drawings where it's referenced here, Carboline Carbozinc 11 primer. The appearance of the coating itself may well give a clue as to exactly what exactly has been applied onto the component itself. When freshly applied, these zinc paints exhibit a smooth beige or yellow appearance, but noting that this can become darker when exposed to elevated operating temperatures. It can be similar in appearance to the grey zinc phosphate coatings and primers, where the zinc is actually present as a compound rather than the elemental condition. And these are largely regarded as inert from either liquid metal embrittlement or indeed the infusion, which we've seen here. And naturally, the colours which we're talking about here makes it readily distinguishable from the red oxide primer coating that's traditionally been used on pressure parts on their transportation from the workshop to site. Where there's any uncertainty with regard to the nature of the coating which is on the surface with regard to elemental zinc, then analysis of scraping should be performed to better understand exactly what you're dealing with. And it's also significant to note that the integrity concerns we're talking about here are confined to the weld heat affected zones. This is where the zinc penetration is significantly greater than remote from the weld. Effectively, operating temperatures do not encourage the infusion which we're talking about for most of this presentation. The observations, the events which we're talking about here are associated exclusively with those high temperatures up above 800 degrees centigrade, which we've seen during the welding process. Furthermore, any remedial work on zinc coated systems, the surface should be ground back to bright metal for up to 50 millimeters away from the weld preparation, so a couple of inches away, to really ensure that there's no risk of getting zinc infusion or liquid metal embrittlement or anything taking place. And where replications identified a dark band of what we would now consider to be creep weak material, then the grinding out of to clear out that banding it would be prudent, and also to monitor the condition of the components at this position at any future overhauls. So in summary, the surface replication of high temperature components fabricated in grade 91 on UK CCGT plant has revealed a dark etching band adjacent to welds, not just on one site, but on multiple sites. The dark band itself is relatively shallow, it's confined to the weld heat affected zone, and with extended surfaces often associated with premature creep cavitation. It's noted again here, important to note, that the zinc infiltration occurs during welding. It is not a service-related effect. On-site and laboratory analysis that we've undertaken at the Technology Centre has confirmed that this dark band in the heat-affected zone is due to zinc infiltration, not liquid metal embrittlement, and it's always associated with the use of a zinc-based weldable paint primer that contains elemental zinc. And it's also worth noting at this point that not all zinc coatings are bad, but the assessment of the coating itself is prudent just to ensure that you've got a good zinc coating and not a bad zinc coating. And it's also found from our experience that the presence of zinc potentially makes the material, the grade 91 in this particular case, more susceptible to creep damage, almost seeming to act as a metallurgical notch within the component and prompting crack initiation. It's also worth pointing at this that within the Technology Centre, approaches have been developed to address the considered risk of damage, which we've identified through the various investigations that we've undertaken. And with that, I'd like to thank you for your attention, and hopefully that was a useful presentation.
Paul, that was excellent. Thank you, and thank you for being exactly on time. And for the audience, we should say that you had made a similar presentation for the European Forum back in May, and at that forum there was a lot of questions that could have led to some follow-on, and so there's a couple of questions along that line. But just let me ask you initially whether there has been any investigation since the May meeting in terms of identifying the extent in terms of the HRSGs, which is main interest here, in terms of manufacturers or constructors or anything like that that can provide a sort of level one approach for us before the nice steps that you indicated.
Yeah, there are certain manufacturers that or suppliers of kit which have used this paint with the elemental zinc within it. Not really appropriate to highlight them in there, but certainly look at the drawings. You know, the example shown in one of the slides highlighted that was bold as brass on the drawing that would be used. So we're aware of at least one manufacturer that has used it. It's very much buyer beware. You know, make sure your quality controls in place to ensure that you know what you're getting. Ask the question if you've got any concerns about the coating that you're seeing on the component itself. As highlighted, look to get it analysed and put it in your procurement specification as well. I mean, okay, maybe the horse is bolted if you've already installed a component with this these on, but certainly if you're looking forward, then make sure that procurement spec makes that line in there.
Barry, based on one of Paul's colleagues' question to me a month or so ago, maybe a little more, I polled folks at a number of the HRSG manufacturers,
Yeah.
asking the question of what are they doing to avoid this problem. And the answers ranged from we never heard of this problem to we tell people to, like, brush it off before they weld it.
Yes.
There
Yes.
weren't any real, what you could, I don't recall there being an answer that gave me a high level of confidence that it was not any kind of problem for that manufacturer.
Yes, Bob, it was that was exactly where I was going trying to take Paul, to say that since that May meeting, you and I have asked a few of the manufacturers and a few of the constructors about it, and generally the answer is the same as you just indicated, Paul.
Yeah, I mean, they say there's certainly one. There's probably a couple of manufacturers out there which have it, which use these kind of paints. They can be used with caution, but it is buyer beware. If you've got this kind of situations developing, and if maybe you have a component failure which then washes onto a component which has been painted with zinc, and you decide to put a weld overlay, then again you leave yourself vulnerable at that position.
Yes. Yeah, exactly. So, Paul, there's a few questions here. I'll read them out. The first one's from Yefin Kashler, and he asks if a zinc-based paint is common, but we only know of a few failures, is it really a root cause of the failure?
Well, I'm aware of only one which has been linked to it. There's a couple where it's been a little bit tentative, and I don't think necessarily convinced that it's been a contributory factor. I think it's probably been a primary factor that's been responsible for it. The one example which I showed from mainland Europe is the only one that we're aware of. There may well have been other issues playing in there. What we have seen is when the guys have done this analysis of the surface replicas, they found cavitation within the darkened zone at a position or at a time much earlier than they might have expected to have seen it. So you've already started the creeps process in advance. How that impacts upon the bulk of the material remains to be seen, but whether it does serve as a metallurgical notch, I guess it's a matter of do you feel lucky? And for us, I think removing the material seems to be a prudent move, and to monitor it going forward.
Yes. The next question, Paul, is from Steve Freitas, and he wonders if this could be related to gate valve seat ring failures that EPRI investigated. I don't quite understand that. Do you understand it? Maybe we'll have to ask Steve to verbalize it for us.
Without an understanding for what the background is to that, I'm afraid I can't provide an answer on that, Barry.
Yeah, yes, exactly. So, Scott, can you open Steve Freitas's line, please?
Good morning. Thank you, gentlemen. I really enjoyed that. There was some papers and articles a few years ago about overlay failures on seating components and valves, and that was a topic of investigation by EPRI and discussion in the HRSG users groups. And just I wonder if, thinking back, maybe those components may have been zinc coated in their processing and contributed to this failure mechanism. Thank you.
Yeah, no, it's possible, Steve. Again, without the details of the component itself, but it would be possibly an area of investigation. It's like a lot of these things that once it's identified, you can then backward or step back through previous failures and perhaps identify some early indicators which went missing.
Thank you very much.
Thanks, Steve.
Yeah, maybe outside of the meeting, Bill Carson could let us know, could let Bob or I know, and we'll pass it on to you if there's anything relevant. The next question is from Dennis Poulos. Just to be clear, he says, when these are finding zinc in the heat affected zone with issues, creep issues, or what are they doing? Grinding out the welds and heat affected zone and re-welding, or something else?
Local grinding is my understanding that there's been implemented there, and It's relatively shallow. You know, for the grade 91 components, we're looking at typically 200 microns in thickness. I'm afraid I can't work backwards into inches and mils. I liken it to be able to speak two languages, but not being able to translate between the two.
Yes.
But you know, they're relatively shallow in terms of what's in there. So local grind out is often enough just to remove the features themselves, and then there's often enough wall thickness left in there to withstand the creep loads. But it does need to be monitored going forward.
Yeah, thank you.
Of course, that's prior to failure. I mean, crack initiation. Is that correct?
We haven't seen any failures with it. So or
Yeah,
put it this way, not seen any in the UK. There's only one example that we're aware of where it's been implicated. And again, I think the jury's probably out with that. If you've got a second failure, you can then start building up a population. At the moment, we're not quite sure what the loading is on that particular component that may well have contributed to enhanced degradation. What we are aware of is what we've seen on several sites in the UK where that dark band has contained cavitation within it, damage at a time much earlier than we would have expected.
I see.
Good. So Paul, there's a question here from Tham Telvan. I'll read it out, and maybe Jeff Henry has some a comment about it, and maybe you can address the European standard situation. But Tham says, if the zinc-based paint creates such a metal problem, why can't ASME or BS31, an American Welding Society code committees, put out a notice, you know, not to use zinc-based paint and I would add, similar to what you indicated in your presentation, within the Uniper specs or something like that. So maybe you can comment on the European, or maybe you know about the ASME or BS31, and maybe Jeff knows something as well.
I'm not involved with any committees, Barry, but my guess is that once it starts entering the committee stage, it sort of takes a bit of time, a bit like turning a tank, and it takes some time to sort of finally come out the other end. I think it's a very valid statement from Tom in terms of the like a degree of urgency to try and sort things out. Within the UK, people are familiar with the experience, and the procurement specifications have generally been updated in the same way that Uniper has. You know, it's not a secret in that respect that this isn't necessarily a good place to be with the with these zinc-based paints. If you do have them, then you can handle it, but you do need to exercise caution. Pretty much, I think, as Bob indicated, that you prepare this as you would do with any galvanized coating. You know, that's considered good practice.
Yeah, right. Is Jeff Henry still with us, and does he want to make a comment?
I don't think he's on, Barry.
Okay, I don't have. Okay, so he can always come back. So there's another comment and a question from Robert Threlkeld. Great presentation, he says. At the plant management level, this would not be an issue. They would know about it. Plants will hire welding contractors for many issues at a plant, but I'm not sure many welding contractors would know about the welding issues around zinc.
I think it's a fair comment. I think it's a very good point raised there. You know, if you like, the more people that engage in meetings such as this, people are aware of it. But as the artisans working on site are perhaps more distant from that, more remote from that kind of advice and recommendation. And unless it's fed through to them, then you're exactly correct. I would say there has to be a risk associated with it. And once again, I guess it's down to local supervision and quality control to manage that risk.
Okay, well, I was just going to say I don't have any more questions, but one just came in from Craig Degnan. The zinc band lies right over the type 4 position. Even if the zinc does not initiate cracking, it masks what is going on in the type 4 region.
I think that's a fair comment. I mean, Craig's got experience with both, and the Type 4 position was raised by Jeff in his presentation. It's long been recognised, and it is sometimes that question of trying to break the two down. You've got two populations, and sometimes one overlaps on the other.
Yeah.
I think the damage that we're seeing looks like, for what I've been informed by the guys looking at the replicas, looks subtly different to what you see from the classic Type 4 cavitation.
Yes, right. So I don't have any more written questions, Paul, unless Scott has some more. And I just wondered whether, as we have a few more minutes, whether anybody wants to ask a live question. Just you can raise your hand if you want to ask a question. Is there anything? Are there any other questions there, Scott? I don't see any.
No, not at the moment.
Okay.
There are a couple of questions that were submitted with registration that might be worth a few minutes. Jeff is gone, but
Yeah.
there are other metallurgists here that I think can answer a couple of them. One, I think is relatively important question. It says that ASME requires post-flow heat treat in 91 alloys, but field heat treat often has questionable results. Is the use of nickel chrome alloy without heat treating acceptable for, well, he says for superheaters, but I suppose that would mean for P91 components. Any of you metallurgists have any comments on that?
It's not really my field, but I'm aware that we've used Inconel cold weld repairs on grade 91 components in the UK. I think there's always the question of whether it does start to encourage creep around the edge of the base material, and once again that's been a monitor through replication. So again, I think it's quality control, like most issues on repairs, is central to the success of that. And I think an EPI project looking at that as to sort of optimizing the parameters for doing the repairs.
Yes, there's Paul. There was one other question that came in before from Jim Anderson, and I was looking for him, but I noticed he's just come back. So maybe Scott can just activate his sound if Jim would like to say something.
I guess I'm not familiar with the question. I didn't put in a question this call, or was this from something else?
Jim, I just saw one that you'd mentioned asking about the extent of zinc failures. I think Paul answered it, but I just wondered if you wanted to say anything else. That's all.
Okay, all right. That's from when I signed up. Yeah, I just was wondering, if it's widely, if it's a prevalent failure out there in the industry, or where us and our friends over there in the UK were some of the select lucky few.
Yeah, but we haven't seen anything in the UK, Jim. It's a fair comment. I think it's recognising that there's potential there, and to act accordingly with a degree of caution. I'm not suggesting ripping out all the components which have had elemental zinc paint plastered all over them in the workshop. We're only aware of the one incident where it's been implicated. So there may well have been other mitigating circumstances as to why it occurred as it did occur. But in the UK at the moment, to say all we've seen has been the signs of the creep damage, notwithstanding the earlier query that perhaps there's a sort of bit of masking of Type 4 and vice versa. So we're keeping a diligent watch on it, I would say, rather than necessarily having experienced any failures or any signs of cracking. At the moment, it's purely in the cavitation stage.
Yeah, hey Barry, this is Ben Ruckty. I just want to comment on that, from our experience here at Structural Integrity, if I can.
Yeah, go ahead.
So hopefully you guys can hear me. I'm on my computer here, so hopefully doesn't sound like I'm in a tin can. But we have certainly seen some examples of this, exactly to what Paul had mentioned, where you kind of see a vanilla looking coating, and where we have seen cavitation in the type 4 region. What I would say that we have seen here, again within SI, is it's generally on shop welds, which is interesting. And I apologize, kind of came in here a little bit late, so I'm not sure how that was commented on, but in the examples, 3 exactly that I can comment on specifically, it has been only on the shop welds and not the field welds. But again, seen that metallurgical notch, seen levels of cavitation detected with replication and with some miniature scoop samples, which has also been kind of a powerful way to actually get some physical samples to do some cross sections. But no failures as of yet. Just something to kind of keep tabs on, again, as Paul mentioned, but we have seen it here in the US.
Yeah, I think that largely corroborates what I gave in the presentation, Ben. So it's nice to hear that.
Yeah,
and this is Jim Anderson again. And our experience with it, it was determined to be a minor contributor to the actual weld failure. There are other causes that were much more prevalent than the zinc.
Yeah, thank you, Jim. Thank you, Ben. I see that Ned Congdon has his hand raised. Can Scott activate his voice, please?
Okay, yeah, I'm unmuted. Can you hear me? This is Ned of
Yes.
HRSG.
Yes. Yeah.
Yeah, Ned.
Okay, yeah, Paul, thanks for a wonderful presentation. Really appreciate that. Just a quick question. I just want to confirm that if there is zinc on a surface that is to be welded, if you just grind it off, you're good, everything's okay. That's my question.
I think that's about as good as you're going to get. I mean, certainly you read through the literature, and there's some reference there that even when you grind it away, there might still be some residual, but I would say that's going to be very minor amounts, and it's not a stainless steel. I think that's the key thing. Stainless steels are clearly vulnerable to liquid metal embrittlement, and a couple of examples shown on that. What we're dealing with, the grade 91, looks to be zinc infusion. So you're going to be looking at a quite discrete zone. What we've seen on the examples in the UK, and it's probably been repeated elsewhere, is essentially this dark ring around the weld. It basically follows the heat affected zone around the circumference, and as such, you potentially got a ring of weakness there. Notwithstanding that you've got the flank position being more highly stressed and more vulnerable to sustaining creep damage. So I think what you described there is what we've practiced, which is to remove that zinc coating for up to 2 inches away from the weld, and that just ensures that you're well remote from any problems. If you want to protect it afterwards, after you've done the welding, you can paint it back up with the same material, and you're covered. It's not an operational effect. It is purely during the higher temperatures you see during the welding process.
Paul, is grinding necessarily the best method to remove it? Because as you said, the grinding will probably leave some residual because you're stirring it up, right? Rubbing it in. Would there be a problem with using a solvent that would remove the paint, like lacquer thinner or brake cleaner, or would those compounds tend to create other problems?
I've not tried them, Bob, so I couldn't pass any comment on it. It may well work. It may not do. Again, I can understand where you're coming from, that the carrier compound for the elemental zinc may well dissolve and be readily removed from it, and that may well be a more effective approach than the technique. But I think that would need to be proven, just to give you confidence that what you're doing.
Well, usually these protected surfaces are already finished for the weld prep, so it's a little troublesome to go grinding on them and disturbing the geometry as well.
Yeah, well, at the weld itself, and again, the fusion boundary itself achieves a temperature high enough to vaporize off the zinc, so that's not a problem. It's in that the edge of the heat effective zone, the infusion. So it's the weld prep itself that you'd be looking to clean up.
So Paul, there's a couple of other questions here. The first one from Pavel Kotovic is a variation of the first question that I asked you. Is there a trend of zinc-coated prefabricated components coming from certain countries of origin, Korea, China, etc.?
I can't comment on that, Barry. I've not got the information to support it one way or the other. I mean, it's an interesting question. It's a good question. And again, I think if you put it in your procurement specification, then you should avoid getting anything of that nature. But also, transportation by sea is going to expose it to certain environments which you may well want to protect the component against.
Yes. And those.
So, hey, Barry.
Sorry, go ahead.
Hey, sorry, I just want to comment on that. So this has been again from SI, and so I want to be clear that that's an excellent point, and I think Paul, you said it well. Is there's to me there's a big question mark on what is being supplied, and again from our experience, it's pretty fascinating in that again the damage that we have seen has only been on shop weld. So the question that brings up is, okay, if it's on a shop weld, you make the weld obviously in a shop. Presumably, it is not coated at the time, and it very well could be. So I think that is, that's something that we have to kind of consider as well. There's obviously then the follow up when you bring something to the site that is, then coated. How do you address it there? And one of the things we've seen is, to Ned's point, is the actual prep, that's done for things like inspection. Pretty fascinating where, if you go through and you blast the component, it's seen some service at say 1050 Fahrenheit. You go and you blast the surface. When you test that area with an alloy analyzer, X-ray fluorescence, you can still pick up zinc. Now, if you go and grind, you're doing hand prep, some of the cases that we've seen is that now there is no zinc. So, again, I think we just got to be a little careful on there are probably a variety of ways that this can happen, and it certainly is very dependent on certainly where it's coming from.
Yes.
And I think we got to look to kind of figure some of that stuff out behind the scenes in terms of the procurement side of the world. So anyway,
it's certainly an interesting point, Ben, about the difference between a workshop weld and a site made weld. Again, I can't comment on that. I've not got that information. That's something which I will go back and explore in more detail with colleagues that have been looking over this. I think it's a very valid point.
Yeah, so Paul, all these questions and that one are similar to what we had in May. And Bob and I were wondering whether there's anything that we can do through these HRSG forums, because as you know, we run this one, we run one in Australia, and we run one in Europe. And if there's any sort of survey or something that we can provide some sort of level 1 guidance here, it might be very useful.
I think the first part, Barry, is what yourself and what we're doing in terms of raising the awareness. You sort of 200 plus engineers on the call today, probably similar number of previous ones, and I think it's raising awareness and the approach is taken to manage the risk. It's not necessarily a bad thing. You're not going to throw your plant out just because you said just go the zinc in there. It's I won't say it's recoverable because it's just a fairly minor trait in there, and we still don't know absolutely whether it has longer term implications, or we've seen the perhaps the start of something which necessarily you don't want to see read the end of the book, which is a component failure.
Yeah, exactly.
One more thing, Barry, and I apologize for jumping in again, but to Paul's point, I want to make one last comment, and then I'll leave you alone. So we talk about, again, kind of masking some of these failures, and you think about things like saddle welds, which is a pretty well-known industry issue where you get, type 4 cavitation on the flank side of the joint. We had a couple of cases where, there was actually a failure that was driven, by the saddle weld. And, at the time there was really no thought around zinc. And, again, kind of looking at the historical, as we ran into some challenges here in this last year, we kind of went back and did a little deep dive on some history. And we actually had that particular sample, and it did have zinc on it. It did have a metallurgical notch. So it certainly brings into kind of, some of the questions here is, okay, well, what overall effect did that really have? I mean, if the zinc wasn't there, and knowing what we know about these saddle welds, probably was going to fail anyway. But again, there's some level of this that we got to keep that in mind too, in terms of what actual effect did that aid in that particular failure. So anyway.
I think it's a very valid point, Ben. And again, I think sort of similar to our lab, you tend to keep the metallurgical samples around, particularly the special ones.
That's right. Yeah.
to go back into the morgue and examine the bodies that you find there, and
absolutely
with current understanding.
Absolutely. So anyway, that's it for me. I'll leave you alone now.
Yeah, thanks, thanks, Ben. No, it's quite okay. Anybody asking any questions, this helps us to provide some overall definition when people ask Bob and I, how do we take this level 1 approach? There's two other quick questions before we finish, Paul. The first one's from Richard Hamilton, and he indicates that some lubricants contain zinc oxide, and is there a risk from these if applied at higher temperatures, or is it just simply a weld issue?
It is a weld issue that's there, but with zinc oxide, I would suggest that that's in the group where it's a zinc compound, not elemental zinc, and it's been elemental in the paint, which has been the where the issues have arisen. So zinc oxide, I do not believe is going to be an issue.
Yeah, and the next one is from another one from Dennis Poulos. Well, will the difference might be that shop welds are machine welded and field welds are hand welded, and welders usually clean their welds before they weld. Just a statement.
Interesting point. It goes back to Ben's issue, I think. Ben's question.
And
There's a hand up also, Barry. I don't know if you see that.
There's one. Yes, okay. I'll do. Just let me do this from Gilbert.
Sure.
From Gilbert Santos, has a comment to qualify WPS with zinc coating, then analyze the metallurgical structure. I think that's basically what you'd indicated, Paul.
I think so. It sounds like it anyhow. And again, it's if there's any doubts on what the coating comprises, then just take a scrape and find out what it's at. That's probably quite a quick check in the chemi lab.
Bob, I don't see a hand up. Can you see it? I don't see one.
Yeah, Eric DuPont. Let me see if I can. Eric.
Oh, Eric. Yeah. Oh, Eric. Okay, go ahead, Eric.
Hi, you guys. Thanks very much, and great to see you, Paul. Thank you.
Eric.
Yeah, hi. My comment, though, is for the previous question, Barry, regarding the use of Inconel filler metal and not post-weld heat treating. And, just for those that might not be aware, the NBIC has instituted some of these non-post-weld heat treated repairs since about 2017 time period or so. And they're allowed with both the Inconel filler metal as well as a type B8, which is the like a P9 versus P91 filler metal. But those are to be done in very certain circumstances, not to be broadly applied. And again, it's only for repairs and again all the construction codes just require mandatory post-weld heat treatment of the 91 and 92. So,
yeah, good. Yeah, thanks. Thanks, Eric, for the comment. And I don't see any more any written questions or anybody with a hand up. And so we finished about 1 minute over, Paul. So that was excellent. So not quite as good as Bob did in the first half, but excellent presentation, excellent discussion. Thanks very much for joining us again.
Good speaking with you again.
And Scott and Bob, I think that's all we've got here.
Yeah, I have